Okay. Yes. It's time to get going. So we're working on chapter 25. It's a very short chapter. We're going to finish it today, maybe a little bit on Wednesday. The homework assignment is due on Wednesday. And after that, we have one more chapter on lenses, which is very similar to the chapter on mirrors. And then we're ready for another lecture. Okay, so we're in this chapter, we're analyzing mirrors. And all the results in this and the following chapter can be written in terms of only two formulas. So the first formula is so-called mirror equation, which is exactly the same shape as the thin lens equation that is going to come in the next chapter. And that equation, I just will write it here, and later we're going to derive it. So the first equation is 1 over dO plus 1 over dI equal to 1 over F. And the second equation is that I divided by HO is negative dI divided by dO, which also is what we call magnification, linear magnification. Let's make sense of those things. So the entire chapter is making sense of those two equations. And actually the same equations are going to be used in a different context in chapter 26. So first, we're talking about mirrors, and those results that we have here are a manifestation of the law of reflection. Very simple equation, which says that if you have a smooth surface, and if you have a light ray coming in here, of course, part of that light ray is going to be reflected. It's going to be reflected somewhere here. And the law of reflection says that the angle of incidence is equal to the angle of reflection. And here, something that we're going to do the following chapters. All angles in optics are measured with respect to the normal to the surface. So here is the normal to the surface right here, and this is the angle of incidence. This is the angle of reflection. They have to be equal to each other. So as a result of this simple equality, we're going to prove the two formulas that are on the other end of the board. So before going to derivation of those formulas, let's first give some intuition about images that are formed from reflection from different surfaces. So starting with a flat mirror surface. So here is a flat mirror, and here is the ground maybe. And usually we're going to talk about objects reflected from those mirrors, and the shape of those objects is going to be always, the shape of the object is always going to be a straight line, an arrow like this. how to form the image of this arrow from this reflecting surface, from this flat mirror. Well, form the image of the tip of the arrow. And in a similar manner, you can form the image of any point of this arrow. So if you look at this arrow, let's say you're going to have one arbitrary light ray emitted by the tip of the arrow. How light rays are emitted by the object? Well, usually those are scattered light rays, scattered light from some external source usually, right? So if you're observing an object like this, and here's the tip of that object, light ray is coming from the fluorescent lights, get scattered from this point, and the light rays that get scattered in direction to your eye, those are the rays that eventually are going to form the image. So let's form that image here on the board. So one light ray may be coming this way, reflected according to the law of reflection. It is going to be reflected this way. Another light ray may be, let's do it this way. And the law of reflection says that it is going to be reflected a little bit like this. Draw it a little bit more carefully so it to fit in the board. Here, this one is reflected this way. And strictly speaking, those two reflected light rays are not going to intersect. So look, what is the philosophy of this image formation? The philosophy is like this. The first light ray reflected means that the image has to be formed somewhere along this line, along the line of the reflected light ray. But where exactly, we cannot say. It could be here or here or here, somewhere along that line. So you need a second reflected light ray, and here's the second reflected light ray, which indicates that the image is going to be formed also along the second reflected light line. But those two lines don't intersect. The rays don't intersect. But their continuations do intersect right here. And therefore, if they intersect here at this point, this is where the image of the tip of the arrow is formed. In order the observer to detect that image, those two light rays, even though they don't intersect, they have to enter the eye of the observer. And here is the observer, the eye of the observer, very wide-eyed observer. So he can capture the two light rays that we're tracing. Now, what the observer brain is going to do, the observer brain is going to continue those light rays, and the brain is going to form an image at the point where the continuations of those light rays intersect. So if this is the tip of the arrow, the next point is going to be formed here, and this point is going to be formed here, and so on, until the entire image is going to be right here. Now, if you draw carefully the reflected light rays according to the law of reflection, you're going to convince yourself that the image that is formed has the same size as the object. So we say that linear magnification of this flat mirror is 1. So magnification 1, this is magnification is equal to 1. The second property of this image, so it is neither enlarged nor reduced in size. It is exactly the same size. The second property of this image is that this image is formed behind the mirror. In other words, it is formed from continuation of light rays rather than light rays themselves. So this type of images we call virtual images. So virtual. Well, why do we call them virtual images? Because if the observer were located behind the mirror, he wouldn't see anything. Behind the mirror, it could be even completely dark. Or if you place a camera behind the mirror, that camera is not going to capture anything. So this is why we call the image virtual rather than real. And the final property of the image is that it is upright rather than inverted. And you see that the image is upright rather than inverted from the diagram. So this exercise is just going to give you idea how we form images from mirrors that are not flat, but have some surface shape. Yes.
Sorry, when I was reading the book, virtual is described by when the distance from the image is negative.
Yeah, we're going to talk about this too. We're going to talk about, so far, we didn't introduce lengths parameters describing the properties of the location of the object, the location of the image, and we're going to do it right in a minute. So now consider a different type of mirror, a mirror that is shaped like this. So the rules are like this. You always have the mirrorized, the reflecting side of the mirror on this side right here. The second rule is that you always need the axis of symmetry of your mirror. That axis is called principal axis of your optical system, of your mirror in this case. And for simplicity, we're going to assume that the shape of the mirror is spherical. It is part of a spherical surface. And let's say that the center of the sphere is located here, which means that the radius of the spherical surface is this length, this distance. If it can be shown with a little bit of geometry and using the law of reflection, the proof is not provided in the textbook, so I'm not going to do it. But you can demonstrate that this mirror has the following property. Any light ray that is coming in parallel to the principal axis is always going to be reflected through a single point. This. So this single point is what we call focal point of the mirror. And notice something here. This means that not only this particular light ray is going to be reflected through the focal point, but any light ray that is parallel to the principal axis is going to be reflected exactly through the same point. Focal point F. Well, strictly speaking, spherical mirrors, the focal point is not exactly a single point. Strictly speaking, in order to have a single focal point so that any light ray parallel to the principal axis to go through, reflected through the focal point, it has to be parabolic shape surface. But parabolic shapes are a little bit more difficult to manufacture. and to analyze geometrically. So this is why we're talking about spherical surfaces. And in order to have pretty much a single focal point with a spherical mirror, you have to restrict yourself only to work with light rays that are close to the principal axis, so-called paraxial light rays. Of course, for optical instruments, you prefer to use a real parabolic mirror that has a single focal point. For us, spherical shape is perfectly fine if you restrict yourself to paraxial light rays, and usually you do it by placing some obstruction that allows only light rays that are close to the principal axis to come in and get reflected. So this is the first easy to trace type of light rays coming in parallel to the principal axis. The second easy to trace light rays is again your mirror, and again the center of the mirror, and again the focal point, are light rays that come in through the focal point. Those light rays are always going to be reflected parallel to the principal axis. So this is the second class of easy to trace light rays. So at this point, it is desirable to define some concepts. So the distance between the focal point and the mirror is what we call focal length of the mirror. And for a spherical mirror, the focal length is half of the radius of the sphere. For concave mirrors, like the mirror that we're analyzing now, the focal length, of course, is a positive number for spherical concave shapes. So this is the second easy to trace light ray. Usually, being able to trace two different light rays is enough. But here is a third easy to trace light ray. So if this is the center and this is the focal point right there in the middle, another easy to trace light ray is a light ray that goes through the center. How is it going to be reflected? Exactly the same way it came from. Again, it is a result of the law of reflection. Theta incident is equal to theta reflected. And even though we don't need more easy to trace light rays, and it is kind of trivial but still useful to keep in mind that any light ray that is coming and hitting the mirror right here in the center, right here in the center, hitting right here in the center, is going to be reflected back in such a way that this angle is the same as this angle. Clearly, this is a result of the law of reflection, so those two angles equal to each other. So those are four easy to trace light rays. Now, so far, we have only one distance defined, the focal length of the mirror, with the convention, with the understanding that that focal length is a positive number. Now, let's form an image using some of those for easy to trace light rays. And by the way, drawing the diagram to form an image is going to be one of the questions on the next midterm. It could be drawing a diagram for formation of image from a mirror or from a lens, or maybe both of them. Let's do one image formation. Let's say that you have a concave mirror like this one. And here is the principal axis. So you always have to show the principal axis of your optical system. And always the image that you the object that you have to form the image for, that object is always on the left-hand side. So let's say this is the center, this is the focal point. Let's place the object between the center and the focal point, and let's figure out where the image of this object is going to be formed. So here is the focal length. Here, the distance between the object and the mirror is called DO. When the object is located to the left of the mirror, DO is always positive number. And for us, we're never going to place objects behind the mirror because there is no point of doing that, right? Behind the mirror, what happens there is nothing interesting. So therefore, for us, the distance DO is always going to be positive. For more complicated optical systems, DO may be negative number. For example, another mirror or another lens may provide an image to be used as an object from this particular mirror. And that image could be somewhere here. So for more complicated optical systems, DO may be a negative number. You're never going to encounter that case because we're doing introduction to geometric optics rather than analyzing complicated optical instruments. Okay, so now let's form the image. So here is the tip of your object. If you consider one light ray that goes parallel to the principal axis, that light ray is going to be reflected this way through the focal point. So you need one more light ray to trace. And let's consider maybe a light ray that goes to the focal point right here. That light ray is going to be reflected parallel to the principal axis. And therefore, the image of the tip of the arrow is going to be formed at this particular point, at the point where the two reflected light rays intersect. Well, you can continue, you can figure out the image of a point that is somewhere in the middle of the object. It is clear that it's going to be formed here and so on. In other words, the image is going to be like this. So let's introduce notation for the distance between the image and the mirror. That distance, call it the image, DI. Our standard notation for the height of the object is HO, and standard notation for the height of the image is HI. So now once we have this image, we can describe its properties. First, what is the linear magnification? Linear magnification is defined as the size of the image divided by the size of the object. Well, in magnitude, that magnification is h(O) divided by hi, and clearly from this diagram you see that this magnification is larger than 1, just from the diagram. You can prove it by looking at appropriate triangles, but again, it is obvious for this case. So it is enlarged image. The second property of the image is that it is inverted. It is upside down. So you have enlarged, inverted, and it is formed in front of the mirror. It is formed by intersection of real light rays rather than their continuations. So images like that we call not virtual but real. And they are real because if you place a camera here, that camera is going to capture the image of this arrow. Or if you place a photographic film or if you place an observer. Well, the observer actually could be some eyeball that is here in such a way to capture the light rays that form the image. So the brain of the observer is going to interpret the tip of the image as the tip of the arrow. And of course, you see that those two reflected light rays are very divergent. So strictly speaking, in order the observer to catch both of them, he needs a very, very wide eyes. Or alternatively, you have to draw a diagram where the two light rays are not that divergent. Yes.
Would the eye need to see both light rays to see the object? Or does it just need one? Like, does the optic have to be big enough to catch both of those light rays, or does that matter?
So the question here is it possible you to see an image just by having one of those two reflected light rays? And the answer is no, you need two of them. And instead, so you either can place the observer closer in order to have, or she to have a smaller, less divergent reflected light ray, or alternatively, you just have to trace light rays that are going to enter the eye. Here in image formation, we are not thinking about the observer at all. I'm just describing you how actually the human eye works, how the vision works. Otherwise, for us, just the diagram is what you need in order to figure out what kind of image is this. Okay, so now we have defined the distances that are formed in this case. And look, in this chapter and the next chapter, all the material is in those two formulas. But those two formulas have to be complemented with the so-called sign convention for the distances that enter those formulas. And the difficult part is to keep track of the sign convention for the appropriate mirror. Different mirrors have different sign conventions. And the sign convention for concave mirror is this. For concave mirror, focal length is a positive number. Well, for convex mirror, it is a negative number. DO for you is always going to be positive because your obligated to place the object to the left of the mirror, di is going to be positive if the object is located in front of the mirror. The image is in front of the image in front. And di has to be a negative number if the image is behind the mirror. So for our case, the case that I have drawn right here, the object is in front of the mirror, therefore di is a positive number. You're going to see in the next case that di is going to be a negative number. Also, HO is always positive because you always place the object upright. But HI is a positive number if the image is upright, like this. For our case, the case that we have drawn, HI is a negative number because the image is inverted. And finally, magnification defined as the ratio of HO divided by HI. The magnification is going to be positive number if the object is upright, again, and negative number if it is inverted, like the case that is shown here. Well, it is clear that we said HO is always positive. We said that for the case here, HI is negative. So magnification for our case is going to be negative number. Negative number, but in magnitude that number is larger than 1 because the image is enlarged but inverted. So look, in all those conventions for the algebraic signs, there is some logic in them. So if you go over letter by letter, variable by variable, you're going to find that it is a reasonable way of applying algebraic signs to those variables. Yeah.
So when do we use the m equals hi over ho versus m equals ho?
Well, I'm going to prove that the same magnification, the same number can be expressed as the ratio of distances between the image and the mirror and the object of the mirror. We're going to prove it in a minute. Before I prove this equality, let's draw one additional situation of image formation from concave mirrors. And that image formation is how you use dentist mirror. So look at the following situation. Here is again the principal axis. Here is your concave mirror. The center of the mirror, let's say, is here. The focal point is right here. If you place the object between the center and the focal point, that's somewhere here, let's say. Let's figure out, using again the 4 easy light rays that can be easily traced, let's form the image of an object that is located there. So the first easy to trace light ray comes parallel, let's say, and goes back through the focal point. The second easy to trace light ray would be a light ray that goes through the focal point. It is going to be reflected. think is not quite right. So we already did this image formation just minutes ago. For a dentist mirror, you have to place your object between the mirror and the focal point. Otherwise, here is the image, and the image is exactly the same like the case we considered. Real, inverted, mummified. Now, let me go back and do the same construction, but now let's place, here is the center of the mirror, is the focal point. Let's place the object between the focal point and the mirror. So this is the case how you use dentist mirror. So in this case, again, a light ray that comes in parallel to the principal axis is reflected through the focal point. A light ray that goes through the focal point. Well, in order to make a light ray go to the focal point, you have to consider a light ray which has continuation that goes to the focal point. So here is this light ray. Its continuation goes to the focal point, and therefore the reflected light ray is going to be parallel. You see that the two reflected light rays do not intersect. But again, the eye of the observer is going to catch those two reflected light rays, and his brain or her brain is going to automatically continue on those reflected light rays. And here is the tip of the arrow, the tip of the object, and therefore the entire object is going to be here. So what are the properties of this image? It is upright, it is magnified, and it is virtual or real. Virtual, because it is behind the mirror where there is no light actually. So for this situation, what is the number representing di? That number is going to be, you have to insert for that distance a minus sign, and di has to be a negative number for this case. The magnification is going to be a number larger than 1 in magnitude, but negative number. Okay, so this is the dentist mirror case. And now let's prove the two important formulas that solve practically all the problems in this chapter, and in the next chapter actually you have exactly the same formulas with different sign convention. So, well, you don't need the proof, but the proof is given in the textbook. Let me quickly sketch it. It is, of course, geometry. So look, here is the principal axis. Here is your mirror. And let's say I'm not even going to show where the focal point is. Just let's say that the object is located somewhere here. And if you look at a light ray that is going to hit the center of the mirror, according to the law of reflection, the reflected light ray is going to be somewhere here, right? So that this angle to be equal to this angle. And therefore, for this case, the image has to be somewhere along this line. This is, the image is somewhere there. Let's, in order to have it defined, let's say that the image is somewhere here. I'm not even going to trace a second light ray to figure out exactly where the image is. Well, if the image is here, if you look at those two triangles that are formed, both of them are right triangles. They have this right angle. And this angle is equal to this angle of the other triangle. Therefore, the two triangles have exactly the same angles. And triangles like that, from geometry, we know that triangles that have exactly the same angles are similar triangles. Similarity means that the ratio of corresponding sides is the same. For my case, this is HO, this is HI, this is DO, and this is DI. So the fact that the two triangles are similar means that HI from the small triangle divided by HO of the large triangle should be the same as DI divided by DO of the large triangle. But remember the convention. If the image is inverted, for inverted image, this is a negative number. Distances here are positive. So to make this fraction positive fraction, I have to insert a minus sign somewhere. But this fraction is defined as magnification. So basically, we have that magnification defined as HI divided by HO is the same thing as negative DI divided by DO. Divided by DO. In other words, so with negative sign, this minus sign is moved there. We have this formula shown. Again, proofs are not necessary, but since we're going to use those two formulas exclusively, this chapter and the next chapter, it is good to show how they come. Now, the derivation of the second formula in a similar manner with a little bit of algebra and geometry is not that difficult to prove. Principal axis, the mirror here. Let's say that you have the focal point maybe somewhere here. Let's say that you have the object and consider a light ray that is going through the focal point. Well, it is going to be reflected somewhere here, which means that the image, yeah.
So earlier you had said that magnification is HO divided by HI, but now you're writing HI divided by HO.
Did I say it is? Look, it doesn't. I may have said that, and that is clearly wrong. So magnification should be the ratio of the image to the size of the object rather than other way around, right? Magnifying something means that the image is larger, which means that if I said the opposite, I was wrong. But at least what is on the board is correct. But good to keep in mind that, words can be misleading, while formulas, right? This is why we prefer to use mathematics and physics rather than talk. Yeah.
So every time a light goes through the focal point, is it always going to create a parallel
always going to be reflected parallel to the principal axis, always, no matter, well, you don't have a second light ray that it comes, but if you consider light ray that comes from the center of the object, it is always going to be reflected parallel to the principal axis. This is the beauty of those four easy to trace light rays.
And then you're gonna have another one after you draw this one.
I'm not going to I'm not going to show another light ray, but if you want to form an image, you can consider light ray that, let's say, is parallel to the principal axis. It's going to be reflected through the focal point. Okay. I'm not going to form the image here. I'm just going to say, let's say that the image is formed, well, somewhere. Let's see, maybe here. The image has to be in such a way that the tip has to be on this, along this line. In other words, this is my HO, this is my HI, this is my DO, this distance is DO right here. This distance is DO, and this distance is DI. In magnitudes, well, clearly HI is a negative number according to our convention, but let's look at magnitudes only of the distances. HI is also here. This is also HI. And by drawing a representation of this HI, I have formed again two triangles that are again right triangles. And again, they are similar to each other because they have equal angles. Again, the similarity means that the ratio of lengths is the same. So let's form that ratio. So let's say maybe forming HO divided by HI should be the same as this. But this length is what? Here is this length. This length is approximately, but pretty accurately, equal to DO minus the focal length of the dealer. So this is approximately equal to DO minus the focal length. DO minus this gives you this. And the corresponding side of the small triangle is approximately again equal to the focal length. So this is approximately equal to the focal length. So we're making some approximations because we're working with spherical rather than parabolic mirror. And this approximation is pretty good, by the way. Yeah.
Is that supposed to be HI over HO, or did you attempt to put HO?
It doesn't matter. I'm forming the ratio of sides of this triangle to the sides of the other triangle. I could have formed the other way around. It's going to lead to the same result. Well, if this is equal to negative DO divided by DI, right? I just have to invert this. So in order to prove the mirror equation, I have to get rid of this HO and HI. And I can get rid of them by taking into account that their ratio is the same as the distances with negative algebraic sign. In other words, this is the left-hand side is also negative DO divided by DI, and the right-hand side I just will read like this. And after that, a little bit of algebra is going to bring this equation to the standard conventional form. So how to do it? Just leave the left-hand side unchanged, DO divided by DI. On the right, write this fraction as the ratio of DO to f minus 1. This. After that, move this minus 1 to the other side with opposite algebraic sign. You have negative dO divided by di plus 1 is equal to dO divided by f. Divide both sides to dO. This negative algebraic sign probably should have been there, but we have it. So if you divide both sides, it is going to, divide both sides to dO, and you're going to have negative. You're going to have 1 divided by di with negative sign plus 1 divided by dO with negative sign is 1 divided by f. So this negative algebraic sign should have been there. So forget about the sign convention that I used. Here I'm doing geometry and I'm working only with lengths rather than the sign convention. And the sign convention is still contained in the previous equation. So if you get rid of this minus sign, everything is going to work out and the result is going to be the way it should be. So here are the two equations. And again, you have to be careful with the sign convention. Knowing this, and since we're out of time, let's see questions and remarks. And the next time we're going to talk about problem number 7 and other problems of your choice. Questions? So for next time, look at the homework problems. So we're to be done with the homework assignment on this chapter. And we're going to solve as many problems as you want. And we're going to start, if we have time, chapter 26, which is lenses, thin lenses, and refraction of light.